Okay, shall we start? えーっと、Okay, Zafira-san, do you have anything you can show me today?
Hello, can you hear me?
Yeah.
Right. Okay, so about the testing, so this is the test that Sumito Moriko showed us last time for the fiction damper, and this is one of the idea. And I also found some reference from the some paper. They can do what's it called, the rotational damper as like this. So maybe we also can apply like this. And also, if you want to add some spring, we can put in the middle of it. So when it deform, it can recenter to original position.
So this spring is your original idea?
Yes, Sensei. I just thinking what we can do to make it to go back to original position. Yeah.
Oh, okay. Interesting.
And I also look up how to design the damper. So first of all, we have to identify the capacity we need, and then the stiffness, including the friction and viscoelastic, and how much threshold drift we need. And we use this formula. And I also already, this is the calculations that I did, and this is the derivation that you asked previously. So it's based on the surface area of the disc and the rotational. And then we calculate the moment of frictions, and also we can identify the force of the friction.
Okay.
Yeah. And then I tried some analysis to find the degree of coupling. And this is based on the Harris result and also Stera 3D. If you can see, the blue line is from Harris and the orange color is from the Stera 3D. So in Harris study, they have lateral load. They already said in the analysis. So from Harris, they have short beam and long beam. So 3.5 is a longer beam, which is 3 meter. And 4.0 model is 1.2 meter beam, which is short beam. And we can see the degree of coupling. I calculate based on the shear in the force and also the base moment of the wall. So we can get the degree of coupling. So short beam have 63% and long beam have 46%. And when I run with pushover 1 over 50 to 1 over 1000, so this is the almost similar to the Harris lateral load. And I also run with Centro and Kobe to check the degree of coupling of the model. And here in the Harris study sensei, they show a graph. So as a reference, so they can show if the degree of coupling around 66% and more, it's called a fully coupled. And if it's less than 66%, it called partially coupled.
Okay.
So
What is the horizontal axis?
horizontal,
No.
this one is this sensei, the member of coupling beam.
Member of coupling. What
Is
does
the
it mean?
it including the strength. If you can see here, it have area and E.
What is the meaning of this horizontal axis?
Horizontal axis. There's a paper. Let me show. Is this one?
Mm.
Is regardless to the stiffness of the coupling.
So this is left part is K multiply alpha multiply H. There are
Yes.
three parameters.
Yes.
And K is what?
K should be the stiffness of the beam.
Stiffness of what?
This one. So it's a geometric parameter.
What is the meaning of this stiffness?
They put here, sensei, the parameter start from 1 and then it increases. K is the value of structure present in parametric study.
But the equation 6.
Six. This also, A is based on the area of the wall. This one. And then A1 should A wall 1 and wall 2. A2 is wall 2.
So this K is used for equation. Could you go up? Equation 4. And where is the equation 3?
Equation 3. 1. Here. 3.
3. Also K is up here. And equation 2 also. And assume the lateral loading on the prototype structure is triangular display load. The height of the additional means all internal forces reactions to lateral displacement of the structure are found using the continuous medium method. Having found the shear force Q in the coupling medium and assuming fixed base conditions, the relative deflection of the end of the coupling beam may be found to be function for triangular loading case. I remember you derived something similar equation.
Yeah, it's based on the tall building book.
Yeah.
Yeah, I think it's very long. This book. It explained in this book, but I think last time I simplified. Let me check. Couple chapter 10. Chapter 10, 400.
Mm, 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 mm. It takes
This
time.
this one I believe so. From this intersection. And this also the key hash from here.
Oh,
Yeah, from this. It's based on the deflection of the
oh, yeah, 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 yeah.
building.
Mm. From equation 10, 10.
Yeah, this is from this book, Sensei, the red color book. But it's a very long to refer to this book. But it actually comes from this book. It explains like it's in chapter 10.
Mhm. So which one is 10, 10? Equation 10, 10.
Let's see.
9.
9. This one calculation
Mm.
10, 10. 10. This one.
Oh, okay. Mm. Oh, okay. Yeah, so there is a theory behind.
Mm.
うん。let me see. I have this book, right?
Yes, Sensei.
Tall building, tall building. Ah, okay, okay. Okay. I will also check.
はい。
So,
A-
うん。
And Sensei, I try to find the one that we discussed before, the ratio of energy dissipation. So first, we want to compare building with damper and without damper. So first of all, we have to find the ratio of energy dissipation from building with damper and also without damper. This is without. And then after we get the ratio of this model, and then we can compare these two buildings. So I compare, and we have now what we just compare simple based on two model. This is from the long beam, which is have low degree of coupling. So we can see here in the low degree of coupling, viscoplastic is actually less than viscoelastic. So viscoelastic dissipate more energy compared to viscoplastic. But if we see the higher degree coupling of structure model, actually viscoplastic act more efficiency, especially at the lower level.
Could you check hysteresis with
Hysteresis?
the
Okay.
damper?
So this one is loading.
Mhm. So this is viscoelastic or viscoplastic?
Viscoplastic. Oh,
Viscoplastic.
sorry. This is SP. Let me change.
Mm. Something strange.
Something wrong. Maybe I should close and open back.
Or I mean time step.
Time step. Okay.
Maybe option analysis dynamic time. Time is 50. Yeah, small, large enough. Yeah.
Okay.
Yeah. Mm, something strange. ちょっとおかしいね。something strange. うん Could you show me viscoelastic?
Okay.
I mean, could you keep this window
Okay.
and
This.
open Stella 3D again?
Okay. Viscoelastic.
Yeah.
This is
Okay.
viscoelastic.
Okay.そっか。おかしいな。うーん。うーん。So viscoelastic, the shear force is over 100, but viscoplastic is 60, 61. And I mean, そうか。And how much shear force for friction?
170.
170. So both response is less than 170.
Yes.
So why two results are not the same?
I think
mean,
maybe because of the stiffness. Because when we put friction, yeah, it's two different stiffness.
How about elastic? Could you check first mode of each model? You can click mode 1.
Okay, this one.
So this is 66 seconds. Something wrong. And how about another one? Both 66 seconds.
Is it because of, let me try. This one, you have to restrict. This one, Sensei? Only X direction?
Maybe.
Four,
Yeah,
six,
2, 4,
seven.
6, 7. Yeah. Okay. Could you click 1?
1.
1?
Okay.
Okay, 2.8.
Okay.
Maybe result doesn't change.
Okay.
Yeah, you can start calculation.
Oh, it's
No, it's getting better.
better. Yes.
Getting better. Okay. 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 Mhm. Mm.
This is
Okay.
viscoplastic. Yeah.
Okay. Mm. 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 Okay. Could you also check mode 1 of this?
Mode 1,
Yeah.
so
Okay.
fine.
Almost the same.
Mm.
Almost same. Okay. Okay.
Okay.
But please check again. Your
Right.
analysis is X direction only or not.
Okay, Sensei. I will redo.
Mm.
Yeah. And Sensei, about this one, I tried to put in this. Is this the graph that you have?
Looks nice.
Yeah. So what I did is, so
Mm.
based on this graph that we
Mhm.
calculated before, and then we want to fix it at 170. So
Mm.
I set this as maximum 170, and it become like this. Yeah. And also KEFF, we calculate based on this formula. So when we combine with friction damper, so we have KB. So the stiffness of the hysteresis become Ka prime. This one. So I input in the calculation here, and then it have the stiffness for this.
ちょっと待ってね。One moment.
Mm.
So this is not a bilinear hysteresis.
How I calculate this? So this is the stiffness based on the viscoelastic. And then when we add the friction damper, we have to calculate new stiffness, which is this one. And this graph is based on this stiffness, but we also can see this is from the viscoelastic stiffness. This is. I try to follow your Fortran, but I couldn't really understand how to code that one. So I tried to use this method. Maybe I can send it to you and you can check, Sensei.
Okay.
Mm.
Yeah, okay. Could you send it to me?
Okay, Sensei. No. Right, that's all, Sensei, for today.
Okay. Could you show me coupling ratio?
Coupling ratio?
Coupling ratio. And you calculate coupling ratio. Yeah, this one. So in case of 1/1000, coupling ratio is 51 for large span,
Long span.
long span. And by the way, what is the meaning of 3.5 and 4.0?
In the Harris model, they give a name for the model. So 3.5 is considered as partial couple, and 4.0 is fully coupled.
Oh, okay. The naming.
the naming.
Okay. And so when you increase drift, this coupling ratio, degree of coupling is getting smaller. Is that right?
Yes.
So it means because the beam is getting damaged.
Okay.
Is that correct?
But since but here is 65. This one is decreasing, but this one is going back to 65.
Why, in case of short beam, degree of coupling doesn't change? I mean, the beam is yielding in case of, I mean, short beam.
I can try to open this. Is 4.0 and still be.
Could you show me the beam?
The beam?
The beam is yielding? Its wall is yielding, right?
The wall is yielding.
How about the beam?
There's no yielding for the beam.
That's why.
Mm.
Even, it's a steel beam.
Yes, it's still beam sensei.
Okay.
Yeah. I follow the capacity based on Harris beam. Yeah. So this.
One moment. I have a visitor. Just
Oh,
one.
okay.
Okay. Could you analyze the long beam case?
Long beam. Yes.
So its beam is yielding.
Mm.
So flexural yielding happens. Okay. This is a reason. So under, you assume steel beam,
Yes.
but the original Harris design, is it steel beam?
It have 4 sensei, 2 concrete beam and 2 steel beam. I can show.
Concrete beam and 2
I
steel.
can show you this one. So they have 2 model, 3.5 and 4.0, and the coupling beam is this. So 3.5 is use conventional beam, and 4.0 use diagonal concrete beam, and 3.5 steel beam is this one, and 4.0 they have more stiffness to increase the strength.
So you analyze steel beam.
Yeah, only steel beam.
Okay. Yeah. So because how to say, this is a long beam, and same shear force Q, and this is a moment, and this length is L. So this moment is QL, right?
Yes.
And if beam is small, even same shear force, moment is small, right?
Yes.
Q, this distance L dash is small. So this beam is steel, so it's not yielding by shear, it's yielding by flexure, by moment.
Yes.
So long beam, you can analyze nonlinear, I mean, deformation. But the short beam, still elastic.
Yes.
So could you go back your slide?
Right.
So it's elastic beam,
Mm.
but after increasing deformation,
Mm.
short beam still continue to be elastic.
Oh, I see.
That's
Okay.
why the coupling, linear coupling doesn't change.
Okay.
But in case of long beam, after getting damage, so I mean, coupling ratio change because the beam is getting weaker.
Yes. I understand.
So this is a reason. Okay, so how to say? So if you put the damper in the middle, it is something beam is weaker compared to genuine, steel beam because you put damper in the middle. So coupling ratio of this case, it's not the same as this one.
Yes.
So how do you evaluate the coupling ratio?
I also still looking for that section sensing because when we put the friction damper limit to 170 and the shear is very small, so the degree coupling will also become very small. So I also want to find how we can compare based on degree of coupling. Yeah, but here that's why now I just compress the ratio of the energy dissipate based on the height of the story. So we can see which floor have more energy dissipation.
So how to say? なんだろうな。So you have two shear wall, right?
Yes.
And this stiffness of wall and stiffness of coupling beam. And degree of coupling, is there any formula in case of elastic? Like the equation you...
It's the same. The total shear times L divided by total of moment over turning.
Yeah. But this KB, you can use equivalent stiffness. Okay, so for example, in case of 1/1000, you can use elastic KB, but 1/200 or 1/100 or 1/50. If beam is getting damaged, you reduce this KB to be equivalent to stiffness.
Okay.
And even you have damper, there is a damper hysteresis, and you can assume some equivalent stiffness for viscoelastic damper. So you can adapt this equivalent stiffness in this, in this formula. Yeah, so first you must evaluate, equation, degree of coupling by some mathematical formula.
Okay.
And by changing KB, you can approximately evaluate degree of coupling after putting damper.
Okay.
Mm. Could you think about?
Yeah, maybe I can relate to this, the one that I showed you just now. 2000, the one that I chose, this one. Maybe I can relate to with this paper because it's related to the
Yeah, degree of coupling is here, right?
and
Degree of
this, they
coupling.
also have stiffness of the wall and the beam. Yeah.
And we can apply equivalent stiffness for the coupling beam. And after you put the damper, you can somehow modify.
Okay.
Yeah.
Okay. I will check this.
Okay. So, Ahmed-san, do you have anything you can show me today?
Yes, Sensei.
Yeah.
Can you see my screen,
Yeah.
Sensei?
Yeah.
So this is what I did so far since our last meeting
Yeah.
on Friday. So I studied the performance, how to develop the performance curve by Kasai method. Your summary, Sensei, was for the steel damper and oil damper. So I tried to propose this for the viscoelastic damper. So this is the system of the steel frame. Consists of many stories with viscoelastic damper, press type viscoelastic damper. So this is the final hysteresis of viscoelastic damper. And the single degree of freedom viscoelastic model, which is divided to the stiffness of the pressing, and this dashboard is for the damping stiffness, the stiffness of the damper and the damping coefficient of the damper, and the stiffness of the frame is divided to shear stiffness and bending stiffness. So we can get the stiffness of the frame from this formula. 1 divided by 1 over K shear stiffness plus K bending stiffness. Then I found how to get the stiffness, the component stiffness of the damper and the press, only for the damper and the press using this formula. This is the stiffness, and this is the energy dissipated by the damper. After this, after getting the stiffness and the energy dissipated of the system, the press and the damper, we can combine this with the multi-story frame to get.
How do you get the equation of right side? Eta A. Yeah, this one. How did you get this?
You mean the reference in set?
I mean, how did you get this formula?
I get this formula from the Kasai reference for the visco elastic damper with the press type. Yes, this equation 2AB, this one.
2A is, I mean, first one is okay. And what is the second one?
Second one is proposed by Kasai. He said that this is the energy dissipated by the system. I mean the damper and the pressing.
But what is the theory behind?
The theory behind this formula, he tried to combine the stiffness of the damper and the stiffness of the pressing with the ratio of the viscous force to the peak elastic force of the damper in this formula.
But how did you derive this formula?
Then now maybe I'll try to find how he could drive this formula.
Could you find out?
Okay, sure, to say.
And yeah, without deriving by yourself, don't believe.
Okay. So after combining this, we can get the equivalent stiffness
Okay.
and the equivalent loss factor for the multi degree of freedom resisting frame and the damping device. I mean the pressing and the damper. Using this K equivalent and the equivalent loss factor, we can calculate the equivalent time period and the equivalent damping ratio for the whole steel frame. So I propose the first stage for the research. We'll find the equivalent damping ratio using Kasai formula and using the normal direct summation and the root summation square. But for sure, I'll change this formula to adapt the viscoelastic damper because this formula is for the hysteresis device and for the viscous damper. Because but I'm still trying to find out to adapt this formula for the viscoelastic damper. And I will plot the difference between the effective damping for each formula, like this one as described here. Yes, in this thesis. And after that, we can find the reduction factor that we can apply to get the normalized shear force using the Kasai graphs that developed by Kasai. We can get the normalized displacement and using the stiffness ratio between the damper and the frame, we can get the normalized shear force for the system.
Well, actually, I want you to obtain the graph, same graph on the right side.
Yes, Sensei.
Yeah, I want you to draw this graph by yourself.
Okay. So this one?
Yeah.
Okay. You mean the performance curve?
Yeah, performance curve. Do
Yes,
you
yes.
have a material how to draw?
Yes, I think I found materials on Google Drive.
Yeah.
But I'm still trying to find out how to draw these graphs. Yes.
Yeah, please study how to draw this graph. Well, maybe
Sure.
starting from hysteresis damper, oil damper, viscous
Yeah.
damper, and viscoelastic damper.
Yes, Sensei.
Yeah. This is a starting point to understand Kasai theory.
Yes. Then later I convert it to the viscoelastic damper.
Yeah. Okay, next time please study how to draw. Show me how to.
Sure, Sensei. Okay. Sure.
And on the Google Drive, I believe you can find information.
Yeah. In Google Drive, I found the data how to plot the equivalent damping using Kasai formula. And how to plot the relation between Kasai direct and root summation square. So I'll try to find out how to plot the performance curve for using Kasai.
Last time I showed you one document which explain Kasai.
Yes, Sensei, but it was the one was in Japanese, so it takes time. So.
No. It was in English.
Do you mean your summary, Sensei?
Let me see.
Okay.
Yeah, in Japanese. It's in Japanese. Maybe in Japanese. ちょっと待ってね。Which one? Kasai method. Performance curve by Kasai method. Yes. Can I share my screen?
Yes.
Oh, no, it's English. It's English. Okay. 1 to 1. So on Google Drive, you can find file performance curve by Kasai method.
Yes.
You can search by keyword Kasai.
Yes,
Find
yes,
this
Sensei.
file, okay. And this is content of the file.
But I think in this file it's not mentioned how to draw the performance curve. I already checked this one.
Really? No. Let me go down. So steel damper. This is a formula. Yeah. So this is the equation. You can get, this is a case of steel damper. Then oil damper. And how to get to equivalent damping. And if you draw the graph, let me see. Step 1, step 2, step 3, step 4, step 5, you can draw this graph. Okay? So this is oil damper. And this is also example how to use this performance
graph to get
the
performance.
So please read whole contents. Maybe you only check first part.
Yeah, I stopped in the first part.
Maybe you stop here.
Yes, and
so could you continue to read?
Yes, sure.
Okay. I think it's a very basic study and very important.
Yes.
Okay. And Ataya-san, maybe you have nothing to show me today.
Yes, since I am just preparing the summary for the thesis.
You must be very busy for summary, and also 4-page abstract.
Yes,
you already showed me 4-page abstract.
No, since I showed only the thesis and for page abstract is not yet, Sensei.
But maybe no problem.
Yes, Sensei.
Okay.
Prepare it.
How is I mean, I forgot the name of the company you will work for.
Life Design, Sensei.
Life Design. Do you have any, discussion with Life Design company? I mean, you are asked to do some preparation? Nothing?
Yes, Sensei. Just at the beginning said to focus on Japanese. The most important thing, and there's something else like a gathering that I have to participate in February.
And how is your Japanese language? You will try.
I am trying my best, but it takes time actually. Not for.
You will take exam, Japanese language test.
To be honest, it was in the beginning of December. So that time I was not as prepared as I am now. So I failed that test, Sensei.
Okay.
I couldn't pass. Yes.
When will be the next test?
The next test is next year, July.
July.
This year, July, yes. Sensei.
This year, July.
Yes, Sensei.
July means you still have, almost half a year, 6 months,
yes,
5 months.
Yes.
Good. Okay, please concentrate on Japanese.
Okay.
頑張って。
頑張ります。
Okay, so shall we discuss next meeting date? Zafira-san, could you send me the PowerPoint slide you showed me today?
Hi. Okay, this.
Okay. And I am very interested in the idea about rotational friction damper.
Okay.
Well, it's up to Sumitomo Riko Company,
Okay, sensei.
but it's interesting. Okay, so let's discuss next meeting. Number 3. So today is 21. Meeting. How about ちょっと早いかな ?6 か。or 7. Wednesday morning next week, 10 o'clock.
I'm okay, sensei.
Ahmed-san, are you okay?
Yes, okay, sensei.
So,
What time, sensei?
10 o'clock.
Okay.
Okay. Seven, 10 o'clock. Ataya-san, you submit paper 2nd of February, and
Sensei.
maybe at the next meeting, control group meeting, could you show me the abstract?
Yes, sensei. Even I can send it before the 7.
Okay. Yeah.
Maybe 5, sensei.
Oh, okay. Yeah.
Yes,
Okay.
sensei.
So see you next week.
Hi.
Okay.
Bye-bye. Yeah.
ありがとうございます。